Okay, this is a problem that I had you try on your own, and this involves drawing the curve y equals x squared. So let's just make this the point. Actually, let's make this the point 1, 1. Let's make this 1 and 2. Same thing on the y-axis. Okay, so we have the line 2 minus y. Well, it's y equals 2 minus x, but you can also think of it as x equals 2 minus y. Either way. And then you're going to have the curve y equals x squared, like this. Y equals x squared, or you can think of it as x equals rad y. And this is being revolved around the y-axis. Oh, and it's the region between the x-axis and the curves. So basically it's this piece revolved around. So it makes like this nifty looking shape like that. It's a cone on top and it's sort of what we call a paraboloid on the bottom. So it looks kind of like a bowl, but it's more like a parabola. Okay? Alright, so how do you find the volume? Well, you can certainly use discs. So you could slice it this way, like that, and these have thickness. You can imagine doing this one on top of the other to form this solid. So each of these has a differential volume, base area, that's just pi r squared, times height, which is dy. Alright, and then you would integrate those. Now before you can do that, you need your r to be in terms of y. Okay, so you're going to try and integrate, but you got to be careful. So for some of the disks, when you draw them, let's go ahead and go back to our graph over here. For some of these disks, when you draw them, they look like this. And the radius is between x equals 0 and the curve x equals root y, because it's connected to the curved surface, and the height is dy. Okay, but that's only true between 0 and 1 on the y-axis. So if you stay under this line y equals 1, all your washers, all your disks look the same. They all have that same radius. Okay? So we're going to go from y equals 0 to y equals 1 using these disks. Pi r squared dy, where r is just the length of this blue segment right here. So this is the radius, and it is root y minus 0. That's the length of it, root y minus 0. So it's just basically root y. Okay, that'll give you the parabolic region. And then you're going to need to get that integral solved. So you're basically just doing pi times 1/2 y squared between 0 and 1. So this gives you 1/2 pi. And then the top half of this thing takes on a little bit different look. Up here your washers, or your discs I mean, look more like this. And drawing that over here, the radius goes from x equals 0 to x equals 2 minus y. And the reason for that is we are measuring between the y-axis and the straight line for this region up at the top where the green shell is, or the green disk is. Okay, so that integral I'll write in green, and it's going to be pi r squared dy again, but the radius is different when you're anywhere between y equals 1 and y equals 2. Example, so.
Well, actually,
So for this disk at the top, the radius is 2 minus y. So you'll run this integral. Alright, so this one's going to give us pi times, and that's really 4 minus 4y plus y squared. So it's 4y minus 2y squared. And there's a plus y squared, so that's plus 1/3 y cubed, and this is between y equals 1 and y equals 2. So if you plug in the 2, you're going to get 8 minus 8 plus 8/3. So that's 8 pi over 3. And if you plug in the 1, you're going to get 4 minus 2 plus 1/3. So that's 2 and 1/3, 7. 2 and 1/3. What's 2 and 1/3? Yeah, 7/3 pi. So that's another pi over 3 in volume. So that's 5 pi over 6 for your total volume. Let me just check my answer. Yeah, that's correct. Okay, now we're going to try it with the shells method, which is a completely different approach, but you'll find it's actually more convenient. Okay, so starting over, this is our graph, y equals x squared. So put our point right here. 2 minus x is this line here. Same closed region. Same solid of revolution. Different approach. So when you draw your shells, choose your axis of rotation to be the axis of symmetry for your shell. So that's a cylindrical shell that wraps itself around the axis of symmetry. So I'm going to draw that shell over here. Okay, so the differential volume is 2 pi r h dr, as we studied in class. And the radius is simply horizontally drawn, so let's assume it's x. So we'll just go with dv equals 2 pi rx. And the height is from here to here, which is between the curve y equals 2 minus x and y equals x squared. So that height is literally 2 minus x squared. And for differential radius, you can see that extending the radius a little bit further out leads me into the x dimension. So I'm going to use dx for that. And this is our integrand. We'll leave the 2 pi outside. We're clearly going between x is 0 and x is 1. And I don't need the r, I've already written that. I wrote that redundantly here. This should just say 2 pi x. So basically we're going to be integrating there's a 2x there, there's an x squared there, and there's an x cubed there. And this is a very simple integral as well. Obviously it's going to give you 5 pi over 6 again, cubic units. Then there's your shells method. Notice we didn't have to use 2 separate pieces to form the solid. We can do it in one if we use the shells method. All right, what's up?